Sonny, are you ready to start?
I am here. Let me share my screen.
Yeah, go ahead.
Okay. Desktop one, share that, and then we're going to come over here and boop. How's that look?
Yeah, all good.
Okay, excellent. Apologies in advance. We're on my personal laptop, so it is, for lack of a better term, a potato. So if anything twitches or looks funny, just let me know. So, so I'm delighted to bring sort of a brief description and maybe an overview of where Pi has been in the last year or so since the last buffet meeting. Obviously, the collaboration has been growing. I think I still have a couple names I have to add to the list that I missed in the last couple weeks. So apologies for folks I haven't actually added to this author list. But largely speaking, it's a group of 8 to 10 models that have been contributing to understanding how photochemistry interacts with observations and how different models parameterize those functions. And so Pi is meant to be a place where we start talking about the nuts and bolts for that process. Obviously, photochemistry is one of a number of factors that can influence the potential observability and characteristics of a planet. So, out of all of that broad planetary space, we're really focused on just the structure, potential hazes, and the bulk composition and trace gas species that you might see in the atmosphere of a planet orbiting some type of host star. So, obviously, you can get photochemistry in a broad swath of parameter space. And depending on what type of target and what type of host, you get different expressions of that interaction. So just to sort of drill down into why uh, I personally thought pi would be a good idea, I wanted to highlight that with a brief motivating example. So one of the things that the community has for the last, say, 60 years looked for is oxygen, and in particular, oxygen in combination with some reducing gas as a signature for life on other planets. And more recently, the community has struggled with a number of processes that could contribute substantial amounts of oxygen to a planet's atmosphere, whether that be through sort of the early superluminous phase of a M-dwarf host star, or whether it's a dry planet like Mars. In particular, there's one really uh, critical photochemically driven uh, false positive mechanism that we've been exploring in the last few years that's derived from the photolysis of CO2 in the atmosphere of a planet orbiting an M dwarf. The planet is otherwise habitable, so temperate conditions, but because of the interesting foibles of M dwarf spectra, you get this predominance of oxygen that's driven by the photolytic destruction of CO2 and the long-lived nature of both CO and O2 in an atmosphere. And Sucrit Ranjan has been doing a great job over the last few years highlighting exactly why that result appeared and was as robust as it was for that very narrow part of parameter space. And it really does come down to a number of factors, not just that we were using different models, but that we were using different assumptions in each of those models. In particular, things like the input data, in this case, the absorption cross-section for water vapor, longward of about 200 nanometers. Historically, it's a very low absorption feature, and so we've parameterized it in a much different ways, ranging from ignoring it to extrapolating to assuming it's flat. But by and large, those approximations didn't really matter for a large part of the parameter space. They only really came into their own when really thrust into the forefront as part of the photochemistry in M-dwarf atmosphere. So Sucrit has shown that the data is important, and I think continues to champion that effort to find and expand our available data resources for modeling exoplanets. The other thing that you can look at, for example, is the input parameters that you've assumed, not just the data that's available, but also how the atmosphere might be structured. where that ranges from things like vertical mixing, temperature, structure, like those are all factors that go into how an atmosphere is described and how it influences chemistry. Uh, and ultimately, all those things assume that all the people who are building them are perfect, but in reality, there's a number of other factors that come into this as well, whether they're transcription rare errors, whether there's erroneous data, whether you've sort of stepped away from self-consistent pressure, temperature, water vapor profiles. Those are all, they all happen. They are all accidents, and by and large, a lot of those mistakes or errors don't propagate quite so substantially. And it's really only in this edge case where they seem to have come into their own and played the proverbial hydra in this mythological tale. Now, all that is to say that all these factors feed into how we look at atmospheres, how we model atmospheres, but it's not really our place to say that we're going to stamp out every error or that we're going to find exactly the correct parameters because we may not know them, right? These are remote targets that are going to be influenced by a number of biases and observational selection filters. And so the differences in data availability drive the need to talk about how our models are built and how we talk about them and interact and compare them between each other. So, for example, between Earth and exoplanets, you might only have a few data sources like astrophysical parameters and maybe bulk composition or the pressure, the presence of hazes. But there's a lot of degeneracies and potentials for missing data observationally or experimentally that drive uncertainties in how we approach these targets. Now, Earth is a whole other kettle of fish. There's a obvious connection to cream I'm going to come back to in a little bit, but the strong motivating factor here is that the uncertainties aren't going to go away and that we need to deal with them. And so I think I referenced it earlier, but we're not really thinking about this in just in the terms of like one particular target. There are obviously examples that we can pull up, but there's a large variety of targets that where photochemistry matters that are going to have uncertainties and need space to talk about how you propagate those uncertainties and how you incorporate them in the analysis that you do. And they range from things like the Earth through time to, hot Jupiters, for example. And there's been a fantastic body of work on a number of these targets and building exactly these same sorts of discussions that I don't have time to talk about, but that if you are interested, you can always come in and I'm happy to regale you with prior efforts and all that I've learned from paying attention to what's going on with those. Now, ideally, each of these targets has its own slice of pie. And in particular, I'd like to highlight the Archean pie protocol lessons from the early Earth, which is a slice of apple pie. What goes into a slice? I've stole this figure from Costas. I'm sorry, Costas, if it's changed in the meantime. I like how straightforward it is. But the idea is that you have a sequence of tests that to support, you know, this wide participation. And if you listen to Linda's talk on Monday, or I'm sorry, yesterday, not Monday, the idea is that you want to make it as easy as possible to get into the comparison and only really ratchet up the difficulty as you need to. And so you want to test the common ground first. But we also need to think about other interactions, in particular climate, where you recognize that the physical connections between processes are going to drive you to need to iterate or to update them based on the results that you've gotten there. Particularly if those differences result in changes in the observables of the system. Now, we've had a number of PI meetings where CAD-ACRA has chimed in and has done a fantastic amount of work in helping us really narrow down what it is that we need and what we think we're going to need and how we can help CAD-ACRA. But really, because we're talking about photochemistry models, getting that climatological input is really, really critical. The other thing that we're going to harp on is that we do care about whether you can see these differences. So incorporating groups like Malbec and I added it later, but Amber's talk on risotto is exactly sort of what uh, uncertainty propagation that we would like to include at some future point. And then obviously the inputs for these models tend to be derived from either physical observations or empirical data sources, but there's also a number of ways that other modeling efforts, particularly 3D models, can inform those physical processes just by parameterizations of multidimensional processes down to one dimension. So the idea of starting these sequence of tests is obviously to bring folks in and ask them what they think the target should look like. And just even the discussion leading up to test zero, where we had folks just, what do you think the Archean looks like? That discussion was incredibly useful for me because I carried into that set of assumptions about what I thought it was, and I just assumed everyone else thought the same thing. And there was a great interaction where Michaela was like, "All right, well, is there biology?" And I just went, "Wait, what now?" And so there's just a wide range, even within a particular description, there's a wide range of interpretations that you can take often. And so I just want to showcase here in test zero things like methane, depending on what you assume about the environment that the planet has, you might have something like abiotic levels of methane, or you might go all the way to, well, obviously there's life there and they're producing methane in abundance. So there can be this wide variety of simulations, even just for what we agree on as a sort of broad top target. And it's not really until you start prescribing additional factors like things like methane fluxes, temperature profiles, that you can start to generate agreement. And you can see here that even going from what do you think the Archean is to let's agree on sort of bulk composition, you start to narrow the field on what the expectations are going to be. Now, and apologies to, I think, PCMG, you see, and I'm not sure why that is over there, but I still haven't figured out exactly what my scripting is doing. So I think that's a bug on my end. And so I say that because it's here as well, but as you continue to narrow the focus, you narrow the field, you continue to reinforce what is ultimately going to be sort of a consensus envelope, not a consensus value, but a consensus envelope where each model produces some result, and the question becomes, A, is that reasonable physically from a physical intuition, and then B, is it even observationally detectable, the differences between these types of simulations. And I think as we continue to narrow the parameter space down, as we add more and more constraints on what we're modeling, we're going to find that we end up in sort of common space that feels very reasonable, that isn't going to necessarily result in strong preferences observationally between models. If it does, then that really tells us that there's something going on that we need to understand in preparation for observations, but it's also something that we can hopefully tie to extant observations to give us better constraints on how models should behave. Again, to back up slightly, there's no like correct answer unless we're talking about matching observations of things like the Earth, where we have very rich data sets. I'm thinking here more of like, are you agreeing with an error with an observation that has larger error bars, for example? Now, I want to point out that, obviously I mentioned CODAGRA. We've had a couple of co-meetings already. We're still hashing out the details there. Yassine has been doing a fantastic job playing an intermediary, helping me like figure out exactly what it is that we need to exchange and how. But some of the tests that we've designed include this idea of an iterative check on pressure temperature profiles in combination with composition. And photochemistry is important for some targets, particularly in that same sense. So the idea is that Pi takes in pressure temperature profiles and then integrates sort of an iterative check in several of those tests to make sure that everything is on a level. And then for COD-ACRA, we can provide things like composition and hazes. Broadly speaking, that's what photochemistry is going to give you, regardless of what your interested um, model dynamic is. So it's going to be a recurring theme through the rest of these connections. With Camembert, I think there's a little bit of nuance there because that slice for many Neptunes or sub-Neptunes is really going to be a departure from more terrestrial photochemistry. And you're going to get into a space where you need to think about things like thermochemistry and how do you interact with between photochemistry and thermochemistry. But because Camembert does have 3D simulations, you can include things like vertical mixing that's parameterized from higher order models. So you're not just by fiat declaring what the mixing should look like. You're actually using physically motivated mixing timescales to drive that parameterization. And obviously, because you're talking about a mini Neptune, compositionally, you could get different types of gases, especially in the upper atmosphere from the lower atmosphere. And then you can get very different hazes as well. They're not even in the same composition, but I mean, hazes are a fact of life for exoplanets. Uh, and we haven't started up a slice for the modern Earth yet because that's a feels like a whale. There's a lot of data there, and I think that there are a lot of very detailed and detail-oriented models that are going to do a much better job. And the question becomes, I think that that's already covered by something like ACCMIP, which is doing fantastic work. So that's a very different pond than the one we're in. But we can still use that to anchor, for example, the model physics that has been parameterized against observational validation with a very rich data set. So we can borrow some components of that and then maybe complement what Cream is doing with some of the work that we're doing. And then lastly, I've mentioned observations a few times, but things like doing simulations of observations and then maybe asking about how uncertainties are propagated can be very useful, both for sort of the numerical model monkey that I am, but also for the observational side of things where you are actually getting photons into some sort of instrument that will have some uncertainty. So the question is like, how do you marry those two together and really understand the parameter space that you're living in to a much greater extent? And so, just in the last couple minutes, I wanted to plug that obviously we were having monthly meetings. I think that's been really useful. Unfortunately, I missed the last one because I was at a wedding. But the next one is just a few weeks away. So if you're interested in doing this, we're very interested in getting a few more people on board. I'm also very interested in getting some folks who are willing to help write. I have sort of hit a wall a few times with that, so any help would be appreciated. We're also looking at the future where we're moving from things like 1D, which is where I think a lot of us are very comfortable, to asking folks who do 3D models, particularly photochemistry for, doesn't even have to be terrestrials, to sort of like look in and see, look ahead with us as to what it is that intercomparison will look like between multidimensional models. And then again, looking forward to starting or continuing intermip activities with a wide range of other exomips. And from last year, we talked about stellar spectra, and that was a big deal, is a big deal for photochemistry. So if someone wants to start a sort of stellar modeling MIP, I would be enthusiastic about hearing about all of that, but time is a premium. And I'm very excited about Tim's planned MIP looking at interiors because interiors feed atmospheres. And I think there's a lot of work to be done to build an integrated model from core to space. Maybe in my lifetime it'll happen, but probably won't be me. But with that, I'd like to say thanks and take any questions that folks have.
Thank you. Do we have any questions? I have a sort of a science question and a technical question. So first, when you showed the profiles for case 0 or case 1, I noticed there's quite a big discrepancy between sort of two versions of Atmos, so UCR and VPL in the upper atmosphere especially. Do you know why that is? So the gray line and the green line, right?
I don't know. I think, well, I don't want to speak to the differences there, but they are diverging more quickly than I had thought, and probably more broadly than I would like. So I think that's the analysis of these differences, I think, is going to be more work than I have done so far.
Yeah, fair enough. I don't want to sort of put you on the spot here, but it's somewhat, I don't know, maybe it could be actually easier because the discrepancy is so big, so it must be something really major. But yeah, I have no idea. So, and also a technical question in terms of like synergy with Malbec, for example. Have you thought about using the same sort of file format for the input data as Malbec does, or do you require something more, something different?
When you say input data, do you mean like for each model to read in?
Yeah, so essentially PT profiles and sort of profiles of chemical species.
So we have input files that are in like a format that is common between the tests, but the issue with a lot of these models is that they have very different requirements for input formats. So we've sort of left it to each modeling group's interest to figure out how to interface between the input file and their model setup. So um, and obviously, I'm not saying that that's the case with Malbec, where every model can take in some uniform input file, but um, from experience, it can be very uh, distinct when moving from one photochemical model to another on how they take inputs.
Yeah, that's fair enough. Okay, thank you. Thomas?
Yeah, hi Sonny. Great talk. Can you come back on the slide with the different planet cases? Thank you. Yeah, I was wondering, so I think there is no super Earth, right? So I was wondering if there will be a specific science question that will be tailored to super Earth. It would be interesting to look at, knowing
It's
like right now that's the only atmosphere where we have the potential int is LHS 1140b. It's anything below mini Neptune where we can have potentially an atmosphere.
how warm is that?
It's inside the habitable zone, so I don't exactly remember the insolation. Maybe Martin on the call remembers
But I
that
mean,
it's habitable.
yeah, my physical intuition is that rocky planet atmospheres are gonna like the span that you get from the solar system, I think is going to be well represented by larger planets, and it's really only when you get to like things that border sub-Neptunes where you have to like have a very serious conversation about, does this assumption break what
Yeah,
we assume about like deep atmospheres, for example?
yeah,
So
because we are right at the radius value is 1.75 Earth radius, so it should really, really limit mini Neptune.
yeah, my physical intuition is if you have a surface, it's going to behave more like a rocky planet. But if
Mm.
you don't have a surface or your surface is at, 3,000 bars, like it's going to behave. I think there was oh man, I'm going to butcher it, but there was someone a few years back who looked at basically if you set your surface pressure beyond a certain boundary, it just doesn't dynamically or compositionally affect the upper atmosphere, the observable part of the atmosphere. Like it basically looks like a mini Neptune. I'll have to dig around for that one. I thought I'd seen that in a paper. So
Okay, and about gravity, because I'm no expert in photochemistry at all, but the higher gravity, can it play a significant role in having the model predicting different things? Or?
I mean, it can a little bit. You're changing your scale height, but gravity varies basically linearly with planet mass and radius as you know, across rocky planet ranges, like some subset of that parameter space. So I think that you're gonna get knock-on effects for changing your planet around a little bit in that parameter space, but I don't think you're gonna get like the same sort of bifurcation that you get between rocky planets and mini Neptunes. Like that compositional divide is also one that's spanned by is also driven by the physics and sort of compositional underpinnings that divide those planets more broadly.
Okay, thank you.
Any other questions? I see that come up with a comment in the chat that the difference between Atmos versions could be due to, well, UV cross-sections.
It's possible. I think they've been doing a job keeping up with things, but again, I'm not going to speak for one model over another. I think that it's probably something that I overlooked in describing the tests. And if I overlooked it in describing the tests, then it's something that's useful as a example of something that we need to consider moving forward.
Mm-hmm. All right. So if there are no more questions, I guess we can move on to the next talk. Thank you, Sonny. So after this very nice slice of one-dimensional pie, we can our next dish on the menu is a slice of camembert. So Duncan, whenever